As a reminder, we finished chapter 2 on Wednesday, and there are 2 class periods between the end of the chapter and the homework being due. So the homework problems for chapter 2 are due on Monday. On paper, physically handed in. If you do work in Excel, if you type stuff up, that's fine. Print it, bring it with you. There's a discussion on turned in assignments on the syllabus. But let's talk about visualization. What does it mean to look at our univariate data? There are lots of different displays. And it depends on whether we have numerical data or categorical data. If we're dealing with categorical data, really, all we can create is a summary somehow. So really, we have to start with a couple of questions. Let's start if we have quantitative data. Sorry, let's start if we have qualitative data. We said qualitative data was really labels, nominal data of some type. Maybe it's somehow slightly more measured than that, but most of the time, if I'm dealing with qualitative data, all I can do. Here's how many people answered this way. Here's how many people answered this way. It's a summary. Now, how we display that summary is important. And you've seen dozens of different examples of this. You've seen pie charts, you've seen bar graphs, you've seen tables, but those are all designed around the idea that we're simply working qualitatively. And there's no ranking to those. So some of the visuals are fairly simple in that behavior. But when we're dealing with quantitative, there are a lot more sub-questions. For example, when we look at the measurement level, is this ratio data? Is this ordinal data? Is this interval data? If it's quantitative, it could be any of those. It could be coded qualitative data, but in that case, I'm really just going to treat it like quantitative data anyway. But now, what units are it in? We've gathered all this data. We have a pile of stuff. What did we count? Money? Is it in dollars? Is it in yen? Is it in kroner? I don't know what the units are, and that's going to make a huge difference. The one that bothers me the most is I have some friends who live in Australia at the moment. The Australian dollar is not the same as the US dollar. They call it a dollar, but it's not the same thing. It's not worth the same amount. So every time somebody says, well, this was $600, I have to go back and go, wait a minute, what's that value in American dollars, and do the conversion in my head so that I have a frame of reference. Is it discrete data or is it continuous data? Because I should have a display that reflects discrete or continuous by the way we write our categories, our descriptors, our subdivisions within it. Have I raised all of the bias concerns that we talked about? The accuracy of sampling. Is there any missing data? How accurate are we? How did we do? How well did we do? But now, let's assume for the moment, I'm happy with the way we collected the data. I know what the units are. I have decided whether this is discrete or continuous, and I can make some sort of visual. Well, then we have to decide what things are important about that visual. What do I want to look at? And with quantitative data, most often, the things we want to look at are center, variability, and distribution. So when I talk about the center, I could ask about how the data is concentrated. Does it tend towards some particular value? How do I measure that value? Because we'll find out in measuring center, there are many different ways to talk about the center of our data, and they're all going to give us different information. Home prices. If I asked you how much does it cost to buy a house in Westmoreland County? Well, that would really have quite a stretch to it, right? Some of the houses out there on Mount Fort Road are expensive as hell. And some of the places right across Main Street, just on the other side there, relatively cheap by comparison. So where's the middle? What's the right measurement for that middle? The home price we see most often? An average. A split the top and the bottom. There are all sorts of different options there. Variability. Well, I was just talking about the difference between the most expensive house and the least expensive house. That's a spread measurement. Is there a lot up here at this high end and a lot down here at this low end? Or is there a lot more in the middle and just a couple on each end? What's the spread of this? And to that end, we get this distribution idea, which is an overall picture of what the data looks like. Is there symmetry involved? Are there just as many expensive houses as there are cheap houses? Are there a lot more cheap houses than there are expensive houses? So I can talk about the symmetry involved or the skew to one side or the other. Are there peaks in the middle? Maybe there's just this giant cluster around 35,000, another giant cluster around 250,000, and there's a dearth of homes in the middle. What does it mean? Maybe it was a really big housing project that built a lot of houses. They're all the same price. They're all right here. Where is that in our data? What does it look like? So we have to start with a pile of data. Here is a pile of data. This particular pile of data describes right there price earnings ratios for 44 randomly chosen S&P 500 stocks. So here's a bunch of price earnings ratios. And over here on the right, we see that they've got this data in two different orders. They've got it in the order it is listed here, originally provided. And we've got the sorted data, and then over here it's sorted differently. So this data that says sorted is sorted numerically. This data was provided out of something else. This data is sorted alphabetically by the name of the company. So that's not even the original order. So let me start with the questions as we ask them. Quantitative or qualitative data? What am I looking at here? Quantitative or qualitative?
PE ratio at least is quantitative.
And nothing else up here is discussed in the title. So I'm going to assume that's the piece they want us to look at. They've even highlighted that column. I'm going to run with the idea that we're looking at quantitative data. If I'm looking at quantitative data, I can now ask, is this discrete or continuous? I think these are in whole number units. So I'm gonna go with discrete. And then I can ask, what measurement level did we get? I always start with the question, is it ratio data? Because that's the most restrictive type. I need to know the most about the data to say it's ratio. Ratio type is numerical, where the actual value of the number matters and 0 has a meaning. If I told you you had a price earnings ratio of 0, that would be a problem, right? But you know what it means? It means your stock is garbage. And something with a price earnings ratio of 10 is half the value of something with a price earnings ratio of 20. And I see Eastman Chemical number 12 is at 16, and Entergy Corporation, Exelon Corporation are both at 10. And FMC Materials is at 20. So I see examples where I can say, oh, the ratio between these matters. I'm going to go with this as ratio. So that means that I can do the most math on this type of data. That's to my benefit as a math geek. All right. They gave me the table in the textbook. This is on page 55 if you want it there. But you also have access to this particular Canvas file. This particular Excel file on our Canvas page. Here, come on, where it says examples in class, chapter 3, price earnings ratio, PE ratios, Excel. There you go. So it's right there. It's the first example. All right. I want to think about the ways to look at this data. I've got this sorted list. I could make some groups here because just looking at this list of numbers doesn't seem to tell me a lot, right? One of the biggest problems with a large amount of data, now this isn't particularly large, it's only 44 pieces of data, but that's more than is comfortable in my head easily. And for a lot of people, the number of data points you can usually consider in your head at one time varies from person to person, but it's usually fairly small, somewhere under a dozen for most people. So having this sorted list doesn't tell me a lot. So let me do some grouping and some summarizing. Okay. Especially in a case where all my data has the same number of digits involved. I can think of 7 and 9 as 07 and 09, and I consider all of these like they're 2-digit numbers, right? Easiest grouping to me is by tens. So let's group this by tens. Now, how do we display that? Let me switch back for a second. I'm going to create something called a stem and leaf display. Now, as I said, this really looks best when all of the data is the same number of decimal places. So if I consider the 2-digit numbers that are in our list, and this is why I told you it's on page 55 if you want to keep flipping back and forth, or if you have the Excel sheet up in front of you, that's helpful. I can say, oh, let's take the tens column and separate it. I'll make all the numbers that start 0 something. All the numbers that start 1 something. And I think the largest number in my list was 59. So I'm going to go with that. And now I'm going to break these numbers up so that I have the tens digit here, and then I'm just going to write the ones digit next to each corresponding tens digit and put a bar to separate those. We've got like leaves growing off of a stem, So off of 0, we got 0.7 and 0.9. Off of 5, there are only two numbers in the 50s range. 50 and 59. There's only one in the 40s range. So over here in the camera, I'm going to write the appropriate ones digit on each of those lines. This is not particularly easy to automate. It can be done. And that's why in the Excel sheet, we're going to see a stem and leaf plot as one of the tabs in the Excel sheet. Now, what did I do? I took our sorted data, which is over there in the first column, and I said, divide it by 10 and round down. So 7 divided by 10 is 0.7. I round down, I get a 0. That's the stem of that number. Then I say, oh, give me the rightmost number. That's the ones digit. So I have the 10s and the 1s split up here, don't I? And then over here where it says stem and leaf, I created the most ugly formula I've ever seen. And I must tell you, I had help. I looked up how to do this. This is a tedious process by hand. The formula is massive. What it does is it goes through the entire list and says, if the stem matches the thing that I wrote down as the stem in this left column here, if it matches that, copy the ones digit on. And repeat that all the way down the line. And I said, oh, okay, well then I need to do it for all the different possible stems. People doing this automation probably took me half an hour to find this one. I hate this. And by the way, this only works for 2-digit numbers. What happens if I have 3-digit numbers? Well, then I'm going to need bigger stems, right? I'm not sure this is the best way to go about this. I've done a lot of these by hand, but I'm not sure that's beneficial. But there is something that is immediately beneficial to me here. I can see the shape of my distribution. I can see center points. I can see some sort of clustering going on here, yes? It's kind of easy for me to say now, hey, look, most of this is in the 10s and 20s range. From somewhere between 10 to somewhere up to 29 is most of our data. And there are a few higher ones and just a couple lower ones. So I can say that this is skewed to one side. Our data goes from 0 to 60, but most of it is between 10 and 20. Not in the middle around 30, right? 0 and 59, the middle should be 30. We seem to be lower than that. This data is lopsided. Okay. That's one version of a grouping. But I like this idea of looking at how often certain numbers come up. You see, I see a bunch of 10s, a bunch of 11s, a bunch of 13s. There are certain repetitions here, right? So maybe it might be better for me to actually look at each of the individual numbers. I'm going to go back to one of my very earliest math courses, and I'm going to make a number line. And the number line is going to go from my lowest value to my highest value. So in this case, it's going to go from 7 to 59. And each time I run into a number, I'm going to put a dot on it. There's a 7, a 9, there are 4 10s, there are 3 11s, and I get again a different look. Now this doesn't group the data at all. This strictly counts it by frequency. Again, this is not an easy plot to make. And it kind of takes a little more away from that idea of center. Right? I don't see a clear center point anymore, do you? I see this sort of smeared out behavior. This data over here on the left, there's clearly more stuff in this 10 to 20 than there is over here. I still see the lopsidedness. I don't quite see the same clarity of here's the middle. But I think this might actually be better than the previous. Again, I have the sorted data, and over here it counts how many times you've seen that in the previous numbers. So that's how it's running this up. It says, oh, just count everything to the right and up and see if it's the same number. And if it is, tell me how many times it's happened. And that's what we plot over here. The X value is our price earnings ratio, and the Y value is the number. And that's how we get dots of 1 and 2 and 3 and 4. None of our data appears 5 times. Questions? On page 58 in our text, there's a dot plot regarding business cycles. And it's showing the length of a business cycle, which they declare to be the distance from a boom to a bust. So how long is a given recession? And the table I actually have up here mentions explicitly this: business contractions, the recessions that we had, starting in 1857 and ending in 2021. How long were they? And up there, where's the Great Depression? 1929. 43 months. That's not even the longest one up there. We think the Great Depression is a huge problem. What's the biggest piece of data up here? It's the largest value. It's kind of hard to tell immediately, isn't it? Just the list isn't enough. But if I slide down here, oh, I can tell you exactly what the largest one is. It's way out here, isn't it? Over 5 years long, 60 months. So now I go back and I look for that 60 something. And I see up here 65 months, 1873 to 1879. 1873 to 1879. Now I need a history lesson. What happened then? So while I like a stem and leaf display, while I like a dot product, I think they're a little too simple. So how can I do this in a better way? What's a better attack? Or at least a potentially better attack? Well, let's decide, instead of doing this by tens, let's make a different decision. Rather than just make the decision, we only divide this up by tens. Let's let the data tell me how to divide it up. Let's make some decisions based on the way the data looks itself. We're going to call those data groupings bins. So I need to figure out what the bins should look like. And this is 100% your choice. There are some ideas on what we should go by, but it's going to depend on the data directly. Once I know how many bins I'm going to use, then I can tell you how big each one should be. Now, the problem is that there's no hard and fast rule. There are a couple of approximations. I always forget if it's an I or an E on his name. It is an E, Sturge's rule. Sturge's said, you know, every time you double the number of data points, you should add another bin. Okay, people, here's an algebra question for you. There's a word for how many doublings we had to do. Think about it. Start with 1, multiply by 2, I multiply by 2, I multiply by 2, I multiply by 2. What's a shorthand for telling me the number of times I multiplied? It's a power, right? When I multiply by the thing twice, I square it, then cube, then fourth power, fifth. So I'm looking for the power, right? I need to know the exponents. Here's the algebra question. Back in my algebra class, they told me a way to get the exponent out of something. There was another word for what that was, the operation that stripped out an exponent. A logarithm. Now, here's the problem. I'm dealing with the powers of 2, right? So I would need to do a log in terms of 2. The log base 2 of n. But I always want to start with at least one bin. So let me take this and add 1. So I'll put a +1 in front of that. That should be my number of bins. My calculator is going to kill me if I try and do this. So let's not do it that way. Let's use the logarithm that's already on my calculator. This is roughly equal to 1 plus 3.3 log of n. And if you look at your calculator, there's a log button, LOG, that stands for the logarithm in base 10. Common logarithms. So this is a rough idea. We had 44 pieces of data in our price earnings ratio, yes? Let's do that. In our price earnings data, we had 44. This is going to give me some really ugly ass decimal. I just need 1 or 2 decimal places here. What do you get? Okay. So I either want to use 6 or 7, right? Because I have bins as a whole number. I'm sorry?
Sorry, I didn't get a put 48, so.
So what do you get here? It can't be that much different. Okay. Still between 6 and 7, right? So I got to use either 6 or 7 bins. And now I would say to myself, okay, let's look at the data. The data goes from where to where? The lowest value of my data was 7, and the highest was 59. So let's figure out how wide each bin should be. How many numbers? Well, I'm going from 59 to 7, start at the high end, work my way down to the low end, and I want to chop that in either 6 or 7 piles. So I would take this range and divide it by 6. If I'm using a fewer number of bins, that's how big each one should be. What's this number? If I wanted to use more bins, I'd get a slightly smaller number. Great. Now here's one problem. My data is whole numbers. Using these decimals is going to piss me off. So I probably want to round it. Round that to 9, round this to 7, maybe round this to 8. Sometimes the boundaries of my bins are more important to be nice numbers. Dividing stuff up by 8s or by 7s or by 9s might not feel right. Let's take a look at what this data, let's use, do you want to use 9 or 8 or 7? Which number do you want to use for our width? Which one speaks to you? Okay, if I use 7, then each bin needs to hold 7 numbers, right? So the first bin, the lowest bin, is going to start at 7. Where does it end? I want this bin to hold 7 numbers. 7, 8, 9, 10, 11, 12, 13. You would say, well, I should add 7. That should be 14. 14 is the start of the next bin. So I want to go up by 7. But that means this one needs to end the number before. Now, the problem is when I do this, what happens? I didn't end up with the right number of bins, did I? I said we wanted to use either like 7, I said, that's what I did wrong. I wanted to use 7 because we took this number and rounded it down for each width, but that's not 7 bins, is it? And I'm going to have data in all the way up to here. My biggest data value, we said was 59. 1, 2, 3, 4, 5, 6, 7. I ended up with 8 bins because I rounded down. That's okay. Again, now I've used whole numbers. These are my bins. But you may look at this and go, I don't like this breakup. I don't like the way these count. Counting by 7s doesn't seem natural. So we could then say, well, maybe we should use 8, maybe we should use 9. But now you have the ability to make these decisions, right? And then we would take our data and sort it this way. And I would simply count how many are in each group. Now, when I do this, I'm creating a frequency distribution. That's what this is referred to as, a frequency distribution. And it's telling me how many numbers are in each of those bins. Well, this really was a frequency distribution. Only what were my bins here? They're just 10s. So if I were to make this frequency distribution using bins of size 10, I should get that again. And that's what I've done here. I've created a bin, goes from 0 to 10, 11 to 20, and so on. Well, I've got really those 0 to 9. See the way they've written bin lower and bin upper up there? Aha, wait a minute. Data analysis histogram. This picture that looks like a bar chart is called a frequency histogram. And what it does is it creates exactly that table and puts out this. But what it says over there is data analysis. Look up at the top here. There's a bar. There's a tab that says data. If I click on that, one of the options all the way over here on the right says data analysis. If I click data analysis, it gives me a list of data analytic tools it can do automatically. Guess what's in there? Histogram. And when I say I want a histogram, it says, okay, where's the data? And I would tell it, oh, use the data in column A. Let me go highlight that data. Boop. Command Shift Enter, it highlights all, Command Shift down arrow, highlights all of those, or I can type in the range manually, hit Enter. Where are your bins? Oh, my bins are here. I think I have to give it the uppers on the bins. Enter. Oh, yes, and there was a label on my bin, so I'm going to check the label box. And now I can say, where do I want the output? I want the output as a new worksheet. I want it stuck somewhere in here. I want it to show me what it does. Well, that's this. That's this table. That's the result it gives me. That's this, that I can also ask for a chart. So I'm going to do that. I'm going to say, I want a chart and I want it in a new worksheet. And when I say go, hopefully this works. Ta-da! Hey, look, bin upper 10 through 60 and more, and then the frequencies, and there's my chart. It did it. I didn't have to do it manually. Make this a little bigger so it's easier to read. Now, one of the important things about histograms is that the white space pisses me off. And by default, we want to remove that white space as much as possible. So in between my bars, I should have no room. So I'm going to click on the bars with a right click and say format. Here. Series overlap. No, I don't want them to overlap, but I want the gap width to be 0. So I'm going to lower the gap width to nothing. And it makes all the white space between the bars disappear. Now, this is where you get to go a little crazy. And here's where there's some drawbacks to this. You could do all sorts of colors and textures and changes in design to this. We've got a label over here that I don't think is very much help. So I'm going to get rid of it. I click on that and I say delete and it goes away and it makes everything longer. I also say, wait a minute, there's nothing in this more category. I don't really need it. So if I go over here into the data, I can remove that and it's automatically removed from the histogram. So we can play with this quite a bit. We can also change the bins, because where did it get these numbers from? I created it. I gave you the list of the bins. So if we went back and did our bins by 7s, we could do this right here. We could do bins by any size we wanted. I originally did bins by 8. There's my bins by 8. And notice, lower end of each bin is a multiple of 8. Here's the result of the output. And here's the same histogram. Well, a different histogram. There's a substantial difference between the way that looks and the way that looks, isn't there? This showed me one big peak. And this shows me a couple of big peaks. I even decided to do one by 5s. Wait a minute, what the hell is that extra thing? In here, in this frequency result, we've got some additional information that I really haven't taken into account yet. We could talk about this in percentage terms. We could ask, what percent of the data have I already encountered? Which would mean I need to add up these things. So let me move this chart for a moment, and let me create a new column. Called cumulative frequency. And cumulative frequency adds up where we are all the way back up to the top. Now, because I want to make sure that that stays the same every time, I'm going to put that one in $signs. So it says add from where we are to the top. And as I copy that down, it gives me everything, doesn't it? That's a cumulative answer. Now I can turn both of these into percentages. All I do is divide by how many data points I've got. Cumulative frequency percent. But notice what happens here. That shows me the percentage of all the data that's already gone by. from here down. This red thing that we saw, this red line is that part. It's called an ogive, O-G-I-V-E, and it measures the cumulative amount of the data that's already gone by, which is why it always ends up at 100%. Way over here on the left, sorry, on the right, you can see the cumulative percentage, and on the left, we can just see the regular frequency numbers. So we've got that. And in our data analysis under the histogram, we have the ability to select a cumulative percentage option right here. So it'll generate that OG automatically. Questions? Hopefully you've seen some of this in the Intro to Data course, in your Intro to Excel course, or in just your regular business courses as sources of the data you've been using. There's another way to demonstrate this. Instead of using a set of bar graphs, you can use individual dots and create what's called a frequency polygon. I hate frequency polygons with the white hat passion of 1,000 suns because they really don't look right, because it looks like when you see a line chart like this red one that we were just looking at, most people assume, see, this is the same data. When you see that, doesn't that look like it should be cause and effect? This data is rising and falling as something happens. We're so used to seeing line charts in terms of time. I don't like using frequency polygons. I much prefer the histogram for the same data. This, to me, reads better. I want to talk more about the shape and more about the way we get that. I will do that on Monday. I will see you all then. Have a wonderful weekend. Please remember to bring your homework on Monday.